So, pumping basics. So, the whole entire point of pumps is to deliver energy in a given volume. All right. Pressure is usually thought of as a force per area, but it's also an energy per volume unit as well. So, the energy gained per unit volume is in pounds per inch squared, or psi. And then pressure times flow is power. Energy over volume times volume over time. So psi times gallons per minute. 1714, that is just a conversion number. All right. And that's equal to horsepower. And then horsepower is the same as watts as far as what we're talking about. That is just the metric version of it. So, a couple terminology with it. Head. Energy per pound of liquid, commonly expressed in feet, representing the vertical height of a static column of liquid, corresponding to the pressure of the fluid at the point in question. In general, a liquid may have three types of energy. That is, the capacity to do work may be due to three factors. So we have potential head. So potential head is the energy of position. It's the work obtained in dropping a vertical distance. Hertz is directly measured in feet. Then we have static pressure head. It's the energy per pound due to pressure, the height in which a liquid can be raised by a given pressure. All right. So right here we have two things. We have a tank. Both are using 1 psi of pressure on them. And then you can see with the difference between, we have gasoline and we have water. So water is only going to go up 2.31 feet, and gasoline goes up 3.3 feet. All right. So, and then we have molasses finally, and that goes down. It's only at 1.54 feet. And this is all due to the fact that they're specific gravities. All right. So you have their horsepower in foot. It's psi times 2.31 over their specific gravity, and that's all based off of water. Again, guys, with this, like we talked about in the spring semester, all these equations with pumps, at this point in your career, it does not matter. All right, but understanding the difference between potential head, static head, and velocity head is what is important. All right. I'm not going to be asking you to solve, horsepower equations right now.
You go back real quick.
Yep.
Okay, I'm good.
Okay. So now we have total pumping head. It's the difference between the energy per pound on the discharge side versus the suction side of the pump. And it's expressed in feet. All right. It's going to go through the actual suction of the pump, like we talked about in the spring semester. This is the suction of a centrifugal pump. This is the discharge. All right. So water is going to be flowing that way. So it's the difference between the energy per pound on the discharge side versus the suction side of the pump, expressed in feet. So ZS and ZD are the elevation in feet to the point of the suction or the discharge measured from the datum plane, usually through the center of the pump's inlet port. All right. So now we have HFS and HFD are the friction loss in feet in the direction of flow to and from the pump suction and discharge parts to the respective measuring points. All right. So let's get into actual pump types. All right. So we have kinetic versus positive displacement. All right. Positive displacement, like we've talked about, we're going to get into that later into the slideshow. These are going to be moving a constant volume. All right. Whereas with kinetic, what's going on with kinetic? What type of pumps are classified in a kinetic pump? These are centrifugal pumps, right? These are centrifugal pumps. All right, so these are not going to be putting out these are not constant volume. So they're not constant volume. What are they?
Like a hose?
Second?
Would a hose be kinetic? Or is that more?
No, that's only going to be working. Hoses are working off either gravity or if you have like a well at home. But like a pool pump is kinetic. All right. And it's basically, you're going to be putting out a constant pressure. Remember, we're in the kinetic area right here. So centrifugal is a kinetic pump, and special effect pumps, ejectors, all that are kinetic pumps. So inside the centrifugal area, we have radical, we have axial, and we have mixed flow. So this is a radial flow, and we have the parts of the impeller.
Excuse me?
Yeah, what's up?
Is it okay if you go back a slide real quick?
Yep.
Thank you.
No problem.
I'm good. Thank you.
All right. Give me 1 second. All right. So let's talk the actual pieces of a pump. All right. There's always more to it than what we just see, but real basic, we have the impeller. We have the eye, and the eye, this is the inlet. This is the suction. All right. We have the volute. And the volute is the area from like here to here about. Whereas this is all considered the discharge. And what's happening at the volute is just as important what's happening in the impeller. All right. Now, the big thing is that we have the impeller, it's spinning in this direction. All right. It's not cupping the water and basically scooping it and moving it that way. It's almost flinging it. All right. If you were to make these a little bit more dramatic of a curve, that's still the way we were going to be pumping. That's still the direction that the impeller is going to be moving. It's not going to be moving in this direction. It's not going to be grabbing the water or the fluid that's going inside of it. All right. So it's going to be flinging it in this direction. So when the water is coming out of the eye, all right, and it's going out in all directions. It's not just coming up and going straight up. It's flowing out. All right. And as it's flowing out, it's getting hit by basically these fins here. All right. And as it goes around, as you notice right here, it's all encased. The impeller is up against the casing. So that's why I said the volute is really important as far as what it's doing. And as all the water is spreading out from the eye, and the impeller is putting kinetic energy into it, it's basically releasing it as it goes through. And that's why it continuously gets bigger. So it's not like over here is where it's actively, like this area right here is not where it's actively sucking. It's sucking on all of these pieces of the impeller. All right. And that's the important thing to see. It's constant. And that's why these pumps aren't self-priming, because they're not going to be able to take in its constant volume, whether it be air or a fluid that is going in it. All right. It has to be filled almost to the top to get a constant, to actually start up and run. All right.
Are radial flow always going to be kinetic?
Yes.
Okay.
So we have horizontal versus vertical. All right. And the only difference here between horizontal and a vertical is just the piping arrangement. All right. So as you can see here with the horizontal, that's a front view. There's a side view of the horizontal. This is still the eye right here. That's still the suction, and we still have the discharge. All right. The only difference between a horizontal and a vertical, as you can see, is that you have the suction and the discharge. But all it did was, is instead of having the suction right there being hooked up, because it has a flange right there, is they just connected a pipe that just went this way. That's all this pipe is. Right? They just kind of like pulled it out and extrapolated it. All right. Now we can have different impeller construction. You can have a closed impeller, which is right here, or you can have a semi-closed, or you can have an open. Mostly what you're going to run into is either closed or semi-closed. All right. Now, going through, you have single suction and you have double suction. And what's happening here is you have your shaft with, this is where the motor would be. All right. And this is still the impeller eye. So all the suction is going through and it's being sucked out that way. Now, a double suction is just what it sounds like. There's two areas, there's two eyes where you can be sucked through. All right. And then you can have multi-stage, where basically you just have multiple impellers going along. So each impeller feeds the next. All right. So before we go on, any questions? See something.
Can you have a multi-stage that acts like a double suction, like they're all pushing towards the middle, but it's multiple?
Like it's basically, oh, so if you had like multiple doubles, so okay, so if you had like single suctions here and single suctions here, and then finally a double suction going and then having its outlet
Yeah.
like that. I mean, you could, but the only problem is that it's not like you're going to get more flow out of it.
Okay.
Really what you want with these things, and that would kind of be running in parallel, which you're not allowed to do with centrifugal pumps. It's not good for it. And that's because of the problem of, you know, they're not really able to. They can run in series. You put one after each other, and that's why these multi-stage work. What you could do is that Yeah, I'm going to say no, that you couldn't have a single on both sides feeding one double. All right. And you really wouldn't see that. You're hardly going to see a multi-stage. Really what it's going to be is just a single suction pump. It's just going to be either operating your saltwater system, or it's going to be running your anything like your jacket water and anything like that for diesels. This is really what you're going to see out there. But the point is, like we talked about before with this, is that you always want to know about the other pieces as well out there. And the importance of that is because you want to be able to singularly identify just by looking at the casing. Like we talked about here, looking at the casing and understanding what's happening inside of it. You know, knowing that something that looks like this is a centrifugal pump. All right. That's the importance, because if something breaks or if this is leaking, you're going to have to know what you're looking at, the parts that you need, everything that you are going to need before even investigating when you go out to sea. You know, you're going to know that you're going to need to put in a new seal, you know, on the shaft over here, because that's where it's leaking from, or there's the gasket that's in between these two portions here. One, you don't want to take a pump offline that's working, it's just leaking, and now make it so that it's not able to work because you took it apart and you don't have the right parts. All right. It's fine when you go into it thinking it's one thing and then finding out it's a lot worse. But when you're just taking it apart because you're taking it apart for discovery, that's not a good way of, at least shipboard engineering is. You want to extinguish all efforts of trying to investigate while the pump can still operate, if that's the only one you have. Oh, and one last piece. Each one of on the impeller, let me just go back, just right here. Each one of these pieces that are sticking up and coming out of the impeller, those are called vanes. All right, so again, you have your eye, and then coming off of it are the vanes. So let's talk about pump characteristics. So as we go through, this is our pump characteristic chart. And these are important because they tell us so much information of what's actually going on. All right, so we're sticking with just the centrifugal pump. And right here is what we can tell is with pressure, and we have flow on the bottom. This dotted line right here is our ideal. All right, this is what our calculations say that we should be getting. This is, you know, what the pump is designed to do. But we don't live in an ideal world. We have our actuality. All right. So as we go and get more and more flow, our pressure starts to fall off. All right. Ever so slightly. Now, the big thing that you can think of is this system characteristics. This curve represents everything in your system downline. You know, it could be the resistance of flow, the resistance to flow of a heat exchanger. It could be going through nozzles. It could be doing all sorts of things that are resisting flow. That's what you should be keeping in mind for system characteristics. But simply put, you could think system characteristics as a valve, and that's your discharge valve, because that's still resisting flow. Is it absolutely correct? No, but it will give you a good picture in your own head of how much your resistance to flow of an outlet of having a valve there. All right. So right now we are operating right here because we take our 2 points and we just match them up. All right. So we notice on the top part, our system gets a little bit wider. Now our operating point is no longer here. Our operating point is there. I'm going to change my color up. Let's go. Let's go green. See how that works. All right. So our system was there, and now it's moved over here. So one thing that's happened is we've lost a little bit of pressure. We might have gone from maybe like, let's say our ideal is 60. So we went from like 55. Maybe we went down to 54 PSI. All right. From just getting a little bit more flow, and we're getting, say we're getting 100 gallons per minute, and this boosted us up to 120. All right. But just a little bit of a loss of pressure. All right. And that was just opening up the valve a little bit more, or, you know, maybe we cleaned out a heat exchanger. All right. Because that's all that can be happening. All right. So you clean out a heat exchanger and all of a sudden you're having proper flow going through it. So now as we open up our system even more, we're way over here. And then we can say where the valve or the heat exchanger maybe got bypassed. So now we're wide open. There is no resistance to flow. And you can see our pressure is way down. Maybe we're now at like, instead of 54, we're at 50. But our flow is at like 150 or so. All right. And then same thing again, you go down. So you could say like this is 100% open of the valve. You could say that's 75%, let's say. This is like 50% open. Get nice and small. We have like 25% open over here. And then last but not least, we have 100% blockage. So we have a 0% open valve or closed. So we blocked the system. There's no flow. All right. And this is the big thing that makes the difference. And this is the graph that shows what's happening. This was a positive displacement pump. We would be breaking everything. We would have pipe breakage. We would have leakage somewhere. Something would basically explode if you let it go. These kinetic pumps, you can let her run at this shutoff head and she won't have any problem. Eventually, because the impeller is putting so much kinetic energy and the fluid is not moving in there, eventually you'll actually boil the water inside of that casing. And then it might explode. But that'll take a long time. All right. But you'll have no flow. You're just going to have this constant pressure. All right. That's the biggest thing. This is shut off head right here. Everybody understanding what's going on this graph? Does anybody need me to go over this a little bit more? Everybody feeling pretty good? All right. Good. I'm glad. So now let's just say that we want to increase our pressure. All right. Increasing our pressure, the only way we're able to do that is to get a higher RPM without changing the pump out, obviously. If we want to keep our pump, the only way we would be able to do it is increase our RPM. But that comes with, as always, other things that happen. We're not going to be increasing our flow. As you could see, from one operating point to another, will go from like what 110 to like maybe 112 or something like that. That's not enough to make a difference. But if we need that higher pressure for whatever is operating downline in our system, we don't care. We don't need a higher flow. We just want a higher pressure. That's what we need to do. And a flow of 110 to 112 is negligible. That could almost be seen as the same in the grand scheme of pumps in the world of that. And again, you can always switch through everything. You don't have to stay in this one spot. As long as you either, you clean out your heat exchanger or you open up your valve a little bit more, whatever you're doing to the pump, that's what's going to be happening. All right. And then if you lower your RPM, same thing. And we still have our shutoff head. All right. So before we go into kinetic, let's take a 15-minute break. Yes?
Okay.
All right. It's 10 o'clock exactly. I'll see you guys at 10:15. All right, we're just waiting on everybody. Is everybody back? All right. So let's continue on with positive displacement. All right. So we have reciprocating versus rotary. All right. This is the big difference that we talked about. This is a fixed volume. Constant volume is no matter what, as long as this pump is running, that same volume is going to be pushed through that pump every single time. So with positive displacement pumps, like I said, we are not constant pressure. We are constant flow, constant volume. All right. So we're going to be sitting on this ideal line. Same thing. But we exist with an actual, this red line. Again, there's our system characteristic line. And that could be anything from, a valve being slightly shut or, just resistance in piping, how long the pipe is, everything along those lines can be system characteristics. Now, as our system opens up, we clean out a heat exchanger. All right, we have less resistance. So our system characteristic line is now less resistance. So we're going to have more flow, but less pressure. All right, so the pressure decreases and we're going to have a slightly more flow. All right, now if we close off the system, if we start to have either resistance to flow or we start to clog up something, we have a C strainer that's getting clogged, our flow is going to go down and we're going to have a higher pressure. Now, here's the big thing is that this is where this chart is different from a centrifugal chart. All right. This can happen. You have a fully clogged sea strainer that's barely letting any liquid through. These two lines will never meet, not on this chart, our actual and what's actually happening in our system resistance. So we end up somewhere in this area. All right. And that's why we have relief valves for positive displacement pumps. All right. So what's going to be happening here is we have a relief valve setting. All right. So the relief valve is set at a certain pressure. All right. Let's call it 100 PSI. All right. Now, this, again, remember what we're looking at. Our blue lines are our system curve. So something in our system is resisting the flow. All right. Maybe someone forgot to open a valve. So what happens is our actual curve here, this is where the pump is existing, is on this red line. And like I said, we have to match those two up. So it actually wants to be way up in this area, but it's brought down because of the relief valve. So all of this fluid, like I said, right here is what's going through the pump. All right. So we can have, let's say, 50 gallons per minute, and that's going through the pump. All right. And going into the system is from our 0 point to our relief valve setting. All right. So let's say 25 is going into the system, and recirculating back from the outlet and back into the inlet of the pump is the other 25. Plus, think about it, you still have a suction, plus another 25, and your 25 of being recirced is now going through the pump again, going for a grand total of 50 gallons per minute. And it's just constantly recirculating like that. All right. And sending out only 25 gallons per minute into the system, because that's all the system can handle because of our system characteristic line. Granted, this is not how the everyday operation of a pump should be existing. All right. If you see this, take care of it. Stop the pump, figure out what's wrong. All right. And if you have a closed off system, it's 100% going to be going through that relief valve. All right. Again, because what we have here is where we actually want to be. And that's matching up with our relief valve setting. And that's why we're having a no flow scenario, but a super high pressure. All right. Everybody get that? Okay, good. So we have reciprocating pumps. All right. And these are basically check valves down here, over here, everything I'm circling in green. That's all our check valves. And these are just, like I said, very basic check valves, only allowing flow into one direction. So we have our single acting, which takes our suction, it fills the chamber, and then it's going to push it out the opposite direction. Very good way of seeing a certain volume is going to be moved. All right. Now, if we take that and we move it to a double acting, all right, so now every single time we move that piston up, a volume of water is being pushed out. We move this piston, one volume is pushed out of it. So for every cycle, we get 2 volumes for a double acting. All right. With a single acting, one cycle is 1 volume. Okay. Does everyone see that? Okay, good. Again, as we're pushing one out, another volume is being sucked in, and it's just going to stay on that, basically that way. All right. One cycle, one volume, one cycle, two volumes. So with reciprocating pumps, we have a simplex. It's one piston. All right. This side is our steam end. That is what's going to be driving it. All right. And then this is our wet end or our liquid end over here. All right. You can have these in single or double acting, vertical or horizontal. All right. Who knows where one of these are on the vessel, on the TSES? Where is this? We do have we do have basically this on board the ship. What system would it be a part of? First of all.
Would it be like part of the boilers, like I'm thinking? Or
it wouldn't be physically a part of the boiler, but it's going to be a part of the steam water cycle.
Okay.
All right. So where in the engine room would it physically be? Let's start there. Let's think about what we have in the engine room. It's not going to be an AMS. All right. So think about your 540 lab tour that you went through.
Or engine room, or
Yep, it's going to be lower engine room. So starboard or port side? What do we think? We got ourselves into the lower engine room.
starboard.
Yep. So it's going to be on the starboard side. All right. And it's the import feed pump. All right. It's located right here, basically. That's the shaft. All right. We have those two auxiliary condensers over here. And that's the import feed pump. All right, and then we have our feed pumps here, and I believe another one somewhere. God, is the other one like behind it? Somewhere around there. And then we have all of our refrigeration system over here. So it is next to the other feed pumps, one way or another. So why is it called the import feed pump? Where we have our feed pumps, these are centrifugal pumps. What's going on here in the steam water cycle? Are we still considered steam?
No.
No. Right here, where are we at? What are we coming from in our feed water cycle?
I mean, that would be fresh.
Say again?
Would that be just water?
It's going to be water. It's going to be feed water because it's our import feed pump. All right. So what is it coming from? What system is before the feed pumps? Put it this way, why do we want the feed pumps so low in the engine room? What's that whole point? Remember, everything has a point in the engine room of placement, of why
Gravity.
Okay, we want gravity. Why so? Why is that? What is it going into? The 2 points of why the import feed pump and the feed pumps are so low in the engine room and what's feeding them is so high in the engine room is very important. All right, we have our DC heater way up as high as it can be in the engine room. And that's a big vessel full of liquid. All right, we don't want something that high full of a movable liquid that can really mess with our stability unless we need to. And the reason is because we want to have as much of that potential head as we can possibly get. And that's what gravity is giving us. All right, so we're gaining all of that energy for free. And it feeds into those feed pumps. It goes into those import feed pumps, and right after that, it goes into the economizer and into the boiler. All right, that's the importance of knowing where these systems are in the engine room and why they have a relationship to everything else. So we do have an import feed pump. It's the Simplex, one piston, goes up and down, and it's used in port because usually we're going to only have one burner on both boilers, and we're just going to be steaming just enough to keep, one, the boilers hot. All right. Two, we want to make electricity, so we still want to run our turbines. All right, our TGs. And this is still going to allow us to move feed water into our boiler at a constant volume. All right. Oh, didn't know I could do that. So then we can have all these different versions. This is single or double acting, horizontal or vertical. You can see that these have basically two ends. All right. And then this one's just motor driven. This would be great if you're doing like firefighting or stuff like that out in the wilderness. All right. Now let's talk about what everybody knows and loves. It's the Wilden pump. All right. That is the, like I believe I explained before, that is the industry name. It's the company that makes this pump. All right. They're technically called a diaphragm pump, but they're really like, you know, just how Q-tip is a brand name, or Band-Aid is a brand-aid, is a brand name. These things are called Wilden pumps. All right, so we have our air supply that goes in. We have our discharge, our suctions on the bottom. All right, we still have all of our own check valves inside of here. And these rubber diaphragms are going to be pushing one way or the other. All right, so this is going to be a double acting. So every single time we have movement, a volume is going to be extended. All right, so this volume is getting sucked in. This one over here is already exhausted, and it's constantly just going back and forth just like that. All right. Now, let's talk about gear pumps. The big thing with gear pumps, they do not send fluid through the middle. All right. The volume that they're sending out is taken up between those gears. All right. So they have almost what looks like a wrong rotation, but they are going in the correct way because the discharge is going around. All right. Now, these will have a driving gear and a driven gear. No sense having both of them being driven since they're gears. All right. The volume is the distance, the area inside of those teeth. All right. Now, this is an external gear. We have an internal gear pump. That's where basically we only have one gear. Now, we have a driving gear and a driven gear again. This driven gear is going to rotate, and this is the volume that's going to be moved. All right. So as this driving gear is rotating, it's going to be moving this driven gear around in a circle. And not only does this area get taken up, but this area as well. And you can see where it's gaining its suction right here. And then we have lobe pumps. Now, these do not have a driven or a driving gear. All right. They do have gears outside of them, but the actual pumping mechanism is not driving the other. All right. So we have our timing gears over here that will keep them timed together. And then you could have multiple lobes. This one has over here, is this example is only 2 lobe. This is a 3 lobe. All right. And then we have screw pumps. And basically the way screw pumps work is it's just the basic way of pumping used to be done. Like with the Egyptians, they had screw pumps. And it's just basically a screw that's just bringing up liquid. All right. Where every single time you turn the screw, it's entrapping liquid between itself and the casing. And that's how these things operate. All right, so this is a double screw, double end with timing gears. This is a double screw, single end without timing gears. And then this is a triple screw, double end without timing gears. All right. And now you have sliding vane pumps. And all what's happening with these sliding vane pumps is that you can imagine each one of these little sections right here, if we blow that up. All right, that's what we're looking at right there. What's happening is you have like a spring right here, and it's riding on it, and you have these vanes. All right, so when it comes in contact with the casing, the spring wants to push these pieces out. All right. And as it's pushing it out, it's creating a sealable area. And now that's where all the liquid is going to be taken up. And then, oops, I hate when I do that. As it comes up in contact with the casing over here, it's going to be pushed down. And now there's no area where the fluid can be taken up. So it's all going to be extended and pushed out. All right. So that's another constant volume because it's not imparting kinetic energy onto it, but it's utilizing a volume to push through. All right. Now, and then we have these liquid piston pumps. They circulate water, acts as a piston, air is drawn into the vacuum and used to prime centrifugal pumps. I have never used one of these. I've always used either just salt water, what have you. We'll go into that in pump operations. I've always been told these things are more, you see them more on like Navy ships and that sort of thing. All right. So before we continue into pump operations, because today is going to be a long day, anybody have any questions? You all good? All right. One last thing before we continue on. Let's talk tests. All right. So this is what we're looking at right now for this semester. All right. So this is today. We're on the 20th. I know I'm screen sharing. What's going on? That was super weird. So this today, the 20th. We don't have class on Monday. I didn't know that when we were making this. So we have a couple options. I have a built-in floater over here. All right. I really don't want to give you the test on the 26th. That's mean it just doesn't feel like it's going to work out well on your guys' end. All right. Would you rather it on Wednesday, the 27th, the first exam?
Sure.
That'd be
works.
better for you guys, you think? Because then you're only going to have that next weekend to study for exam 2. Okay?
Push together anyways, so.
You're going to have to do it anyway?
I mean, the whole thing's like super compact anyways, so
Yep.
might as well.
So how about we do this? Does that look good for everybody? We'll have our review the day before the exam. All right. And that's all we're going to have on exam 1 is these 3 topics: valves, piping, pumps, and pumps op. Okay. And then what that means is freshwater generation 2 are going to be taught, and they're going to be on exam 2. All right.
So for the quiz tomorrow, that's going to be on pumps and pumps ops.
Yep.
Okay, thanks.
No problem. Let me do this real quick. All right. I think that works out best for everybody. Shoot, I didn't want to do that. So this is your official announcement. All right. The 27th. That's going to be exam number 1. All right. And again, quiz tomorrow for that's going to be on pumps and pump ops. All right. Let's go into pump operations real quick. All right. So, general considerations. As always, there's two ways of thoughts with this, guys. You know, when you go out there and if you're nervous and you're really unsure and you don't want to break anything or anything else like that, line up your whole system. I've pretty much done that my entire time. All right. But the proper way we're going to be talking about, okay, with pumps is that there's always two ways of thought with it. Either lining up your full system always for positive displacement pumps. Okay, because remember, that's going to be putting out a constant volume. So that when you turn that pump on, it needs to go somewhere. All right. With kinetic pumps and centrifugal pumps, as we talked about, you can leave that discharge valve closed the entire time. Eventually, the water inside of there will boil, and then that will become a problem, but that's hours down the line. Within seconds of a positive displacement pump, not having anywhere for the fluid to go, you will have breakage. Pipes will bust. All right, they'll pop through those flanges like you wouldn't, like it would just be, it's instant. All right. So ensure that the suction side piping is lined up as intended. All suction connections should be checked to prevent drawing from an unintended location. All right, so if we're moving fluid from tanks, all right, you do not want to, let me draw this out real quick. Very simple. Let's say this is fuel oil, all right? So we have our port 1, port 2, starboard 1, starboard 2, and then we have our day tank. Day tank port 1. And this is starboard 1. All right. The big thing is that when you're taking suction, no matter what, you have to ensure that your lineup is correct. All right, on your suction. If you want to suck from port 1, you do not want to have any of the other valves open. I know that sounds really obvious, but this is something that you should always be double checking, especially with fuel oil. All right? Because there is abilities to go like this and have this pipe right here, and this just goes to deck. That goes to your deck connection. You don't want to pump there. All right? So you always just want to double check your entire system. And I know fuel is the ultimate scary thing to do because you can lose your license so quickly to it. But it's the one that's the most important to be double checking. All right. Even if you're messing around with bilge water or potable water, and especially potable water, where it really doesn't matter. Unless you're pumping into one of your own bilges and you start flooding out a bilge. But it's one of those things, get in the habit now of double checking your lineup. And the best way to do it is to put your hand physically on it. That's the way I was taught. And if you do that and you put your hand on whatever you're doing, that will take care of you in the long run. All right. It's just something about putting your that physical connection to whatever valve you're doing, whatever system you're operating. It will get you to remember that you definitely close that valve. All right. So ensure the suction side piping is lined up as intended. Wherever you want to come from, make sure that's open. Wherever you don't want to go from, make sure those are closed. All right. And then ensure that the discharge piping is lined up and intended. All right. Just double check. You know, doesn't matter if you did it before lunch. You can have some nut job on your boat that just wants to get rid of you. He doesn't care how. Just double check everything. All right, and then be familiar with normal operating parameters. Pressures, temperatures, so abnormalities can be detected promptly. Rule of thumb with motors, guys, motors should not be running any hotter than the ability to put your hand on it. All right, if you burn your hand basically from a motor, the motor is probably, something's very wrong if it's running that hot. But you should be able to put your hand on the motor and it should be running at a nice, good temperature. All right. So let's continue on with a centrifugal pump. So first thing that we have to do is determine which tank we're going to come from. So we're going to be opening up our suction. Come on. There we go. So our suction is being opened. This is our tank that we want to come from. Our suction is opened. Wherever that goes, I don't care, but it's closed. We go into a manifold. All right. That manifold has a valve right here that we're going to be opening, and it's going to be sending it to our pump. As I did this all backwards. All right. That's all of our discharge. I'm sorry. Jeez, guys, I'm sorry about that. All right, so this is our suction over here. All right, and this is our inlet to our pump. This is our discharge from our pump, and this is where it's all going to. All right, now, this, like I said, with centrifugal pumps, when you are going with centrifugal pumps, the big thing to know is that they always have to be primed. All right, centrifugal pumps always need to be primed because they're not self-priming. They're not going to be able to pull in a volume, whether it be air or liquid, and prime themselves. So what you have is your priming line. Okay. Now, if this is a pump that is operated continuously, you stop it for some just general maintenance, whether if you're taking some readings on the electrical part of the motor, which we get into when you get into your second class cruise of what you'll have to do for that. But if you're going to be taking some readings that need to be turning it off, you don't really have to worry about priming. It will still be primed. But if it's been a time where you haven't used it, you're going to have to prime the pump. All right. Now, when you start the pump, notice this is that our discharge valve is closed. All right. So this is a no flow scenario on our chart. We're here. All right, so we're at this dash mark right here. So we're going to slowly open up that valve. And the reason we're going to do that is that we're giving it time to prime itself with our priming line right here. This is like salt water in. All right. And what it's using is using saltwater pressure to put into the eye and fill up this casing. And then as soon as it has that, it can draw a suction. It's just this casing needs to be filled with a fluid. All right. So as soon as that's good, we open up this valve slowly. We move the line. And now that's how we're going to have flow. Like I said, if you're nervous about it and everything else, this valve can just be wide open and you'll be fine. But really, the proper way is to have this valve, this first discharge valve, closed, and then you slowly open it up. All right. And that will help with the priming, because then you're not going to have this entire pipe filled with salt water. You just want to make sure this casing is getting filled with salt water. All right. And once it's filled, it's filled. It's not going to be using any more than you have to. All right. Now, when you're securing these pumps, the biggest thing to do first is close your discharge. And that will help you in the long run as far as you don't have to constantly reprime these things. All right. So now you have nowhere for this to go. You close that discharge, you secure the pump, and then right after that, you close your inlet. So you're trying to isolate that pump. All right. And then you go around and close all your other valves. That's a centrifugal pump starting. Does anybody have any questions with this? All right, everyone pretty good? Okay, good. Rotary pumps, positive displacement pumps. Biggest thing, line your entire system up. Like we talked about, those things will break, and they'll break faster than you can stop the pump. All right, everything's lined up. You start the pump. You fill your tank. Once your tank is filled, you stop the pump. Then you go and close all of your valves. As the animation is backwards on this. Okay. So the biggest thing is that choose a valve on these systems. All right. Usually just do your discharge. Not the worst spot in the world to choose because you're going to be operating next to the pump anyway. But close a valve. And the biggest reason for that is that you don't want any backflow. All right. You want to kind of split the system in half. So turn your pump off, pump's going to turn off. And it's not like you have to wait for these things to slow down or anything like that. They pretty much stop. They're not instant, but it's kind of like a car going from, 60 to 0. It's pretty quick, but it's not like you have to wait for, it's not like it's a train having to slow down. You stop the valve, you close it so you don't allow any backflow. Close your inlet so you know your pump's secure, and then go through the rest of your system and close all your valves. Always secure your valves. You don't want to be in a situation where you're pumping from another location and all of a sudden now you're sucking from somewhere else as well. All right. Steam reciprocating pumps. We have our suction and discharge, our liquid end, and we have our steam end. We have our supply and our exhaust of our steam. This is our steam. All right. Come on. There we go. And with steam, it's going to be like almost like a train. And that's why like you hear like steam trains are very slow to start. And that's what's going on here. This is like our import feed pump. These things will be very slow to start up and then they get up to speed. They're not going to be at a train speed, but they will get to a nice even pace. As you're seeing here, it's slowly speeding itself up. All right, and it's all very mechanical, which is quite cool. This whole shuttle valve right here is all operated just by the steam pressure itself. So now if a turbine feed pump, all right, we have these on board the vessel. This is the exact one we have, all right. I'm not going to require you guys to know how to start this up. That is a first-class cue, all right. But the basic principle is there. You should know that these steam exhausts and our supply for our steam and our suction and where they're located. All right. And we have our discharge for our water, for our feed water right here. All right. So with what's going on here in the turbine feed pumps, these are all driven, and that's what's so great about our steamship is that everything is so mechanical. All right, where you guys get to really see what's going on in it. We have our lube oil supply from our pump. All right, we have our lube oil return in an overspeed trip. Now, this is our steam supply. All right. And our feed water pump pressure discharge. All right. So this is just giving a little bit of the feed water and it's filling this little cavity, just like our regulating valves. All right. This reach rod right here is literally has a handle on it and it will tighten down on how much this spring goes up and down, how much tension that spring is holding. So what that will do is it will basically allow us to regulate the flow and the outlet due to the discharge pressure. All right. Think about it. If you have a higher, more tension on this rod, you're going to need a higher discharge to overcome that tension. All right. And vice versa. So as the pressure increases, now we have this pilot valve goes up from where it was. Let me get rid of my drawings on there. So the pressure increases. We now have lube oil can return. That opened up. So the operating cylinder is decreasing in fluid. The lube oil is escaping out of it. The operating piston drops and decreasing the steam flow. So the steam level is decreasing. Now, since the steam level is decreasing, we are no longer having a higher speed pump. We are now lowering our pressure coming out of the pump itself. All right. So as that happens, we now have lube oil supply now being added to it. And look, so now it's no longer going to the lube oil return. It's filling up the operating piston. And our supply is going to increase, and thus it's going to increase the steam going into the turbine. And now we're going to have a higher pressure because it's going to be going at a higher RPM. And just that keeps happening. All right. And it's going to happen at greater extents where you're going to see governors do almost like this kind of flow to it. All right. Where you have a high pressure and then it goes to a low pressure and then it goes to a high pressure again, but it's not as much. And basically that's how governors work. They're going to slowly get themselves right. We're almost to a point where you're going to have just little influxes. All right. But at the beginning, it's going to be wild. All right. Now, last thing before we go, with spring tension and pump pressure balance, steam flow is constant. Overspeed trip drops operating piston and drops the steam flow. We went over all of that. So let's see. Yes, let's talk about transfer manifold. All right. So this is a typical fuel transfer manifold. With this is the very important thing that you have to understand. You can fill and suck from tanks using the same line. All right. So what we're doing here is these top cavities are going to be opening. All right. And when they open, you have all of this fluid. Let me use green. So this side is broken in half on the top part. And this entire area here is filled with fluid, filled with fuel oil. All right. And then if you open this back valve here, now this entire top cavity is filled with fluid. Now it's going to go into this lower cavity right there. So now it can go onto either side, the suction or the fill, but the fill is now open. So this entire lower cavity down here is filled up with fuel, and then it goes out to a tank. Okay? That's how you can move fluid from one tank to another easily with these manifolds. So these suction and fills are going from a pump. The suction is the suction side of a pump, and the fill is the discharge side of a pump. And these are going to different tanks. This could be tank 1, this could be tank 2, this could be tank 3, this could be tank 4. And these are, you can go either way with these things. It's one line to a tank. But what these manifolds allow you to do is pull from one and discharge to another. All right? So as you're sucking here, this lower cavity down here, that whole lower cavity is filled with fuel. And these valves are stopping it from going back into itself. All right? It's going into the suction side, so this entire cavity, the upper cavity, is now filled with fuel on the suction side. And that's what makes these things so great. You can suck from multiple tanks at the same time, and you could fill. If you wanted to fill, like, oh, tank 1 and tank 2, they have a little bit of fuel left in them. Let's put it all into tank 4. Well, you can open up tank 1 and tank 2's valves on the suction, and then only open up tanks 4 on the discharge. And that's what makes these things so good. And the other nice thing is that it's a low area. All right, they don't take up much room in an engine room. So you're not going to have to go running all over the vessel in order to open up all of the valves at the entrances to the tanks. Because if you didn't have this manifold, you'd have to go to the tank itself and open up the valve there. But instead you have a manifold, so it's a low area. It's all probably, the pump is probably right here. So especially with fueling, you get control of the entire system in one small area. All right. Everybody understand the transfer manifolds? Everyone understand that how all the sections work, everything like that? Okay, sweet. So what we're doing right here is just a generic example. All right. So we're sucking from this tank right here. Let's call that tank 3. And we're going to tank 5. All right. So we're sucking from this tank. We open it up. We go to our fuel transfer pump. All right. And then it's just, you follow the line itself. That's what makes these things so easy with fuel transfers, is you just follow the lines. All right. If there's a valve, open it. If it's a valve that's going in the direction you don't want it to go, close it. All right. Now, if we're coming from the deck, so we're sucking, we're getting fuel from a barge. All right. The barge will have pumps on it. So it's going to come in. It's going to come from the deck, go down, and we have to open up this valve, and we're going to have to open up that valve. All right. Now, we go into our manifolds. We're only filling those 3 tanks. Those 3 tanks are going to get filled at an equal rate. Now, if we look, what we're going to do is we're back feeding the entire system. So that way, we can open up the suction side as well. So now we have more valves open. We have more piping that's open. We can get maybe a little bit of a higher flow. And then we have to just open those 2 valves down here. And that allows us to open up the other manifold as well and fill the ship evenly. All right. If you're filling one side, fill the other. All right. And then bilge, ballast, and fire main. These systems themselves, they kind of operate almost together because you can use fire pumps. Sometimes a fire pump will double as an emergency bilge suction. All right. Sometimes you'll have a ballast pump that will double as a fire pump. Here's a bilge pump that doubles as a ballast. I don't know why that's not typical anymore because of the oily water. You don't want oily, messy water to go into a ballast tank. All right, because you want to be able to dump and fill those tanks as needed. So that's not something you'll see anymore. All right. What you will still see is a fire pump that can take suction from a bilge. You won't use it as a bilge pump unless it's an emergency. And the reason for that is because they can put out a huge volume of water. Okay. So some terminology, sea chest. What are they?
Hold the water.
Exactly. It's just basically a box where water enters the vessel. All right. That's all they are. They will have valves pretty much right on them, or a pipe and then a valve that comes right off of it. You know, that's really what a sea chest is. And let's talk about before we talk about bilge manifolds, let's talk about this. So a bilge in and of itself, like we talked about in the spring semester in class, a bilge is the bottom of the engine room. That is the lowest part that you can go. But you will have something called a not sea chest. God, why can't I just drew a blank. Give me a hot second. Bilge well. So it's a bilge well. Basically, bilge wells are where you take suction in a bilge from. All right. And what you're going to see is that you'll have a pipe that'll enter into this bilge well. And this is going to be the bilge level right here. That will be the steel deck that you'll be able to actually stand on if you go into the bilge. All right. But then these hold about like maybe 10, 15, 20 or so gallons of water in them. And they'll have like a cage on it. And you'll have alarms. You'll have like an alarm here, and then you'll have an alarm here. And this will be your high bilge. And that will be your high because that's really not good. All right. That means you ignored your high level. So basically what you have here, this is your bilge well. And that's where naturally everything's going to be actually like, it's almost like a road where roads are pushing water to the side. So that way it goes into the drainage system. This is going to be pushing water and flowing all the liquid, all the oils, everything that goes and drops into the bilge. It's all going to flow into a bilge well. So this is where you're going to suck from. All right. And, you know, sometimes you'll have bilge wells. Like I've talked about, you can have that fire pump. That's the emergency bilge suction. Those aren't really going to go into bilge wells. If you're using that, you pretty much have a giant pipe with no cage. It's just sucking water and it's putting it overboard because you're in a bad situation. All right. That's a bilge well. Anybody need this up a little longer or can I erase it? You guys good?
You're good.
Okay, cool. So bilge manifolds. The only thing different from a bilge manifold and a fuel manifold is the fact that a bilge manifold will use this style of valve. All right. Basically, they will ride up and down. The disc will ride on the stem. So these can be open, but if there is nothing drawing suction, the valve itself will be closed. All right. The only problem with these is that you don't want to leave them all open thinking that oh, well, I'll draw a suction and whatever tank, whatever one of these bilge wells are filled will, fluid will come through and you'll be all good. The only problem with that is the majority of the time you have a Wilden pump as your bilge pump. So Wilden pumps being self-priming, and they're going to be drawing a fluid, and air is a fluid. That fluid is going to be constantly coming into here, and you're not going to really prime your pump. You're going to be getting like 1/3 of the volume. And it's going to take it's going to take 3 times the amount of time to pump that one bilge well. All right. So good habit as always. Just close them if you're not using it. All right. Ballast manifolds, come on, you stupid thing, will not operate with a stop check valve. Okay? They're just going to be a normal valve. And same thing. Line up your system, but you guys should be set there. All right? Kevin Johnson's computer crashed. Wanted to let you know. Okay.
That was before.
Gotcha. The chat doesn't pop up easily, so if someone sees the chat and I'm not paying attention to it, just give me a shout, guys. Other than that, do you guys have any questions or anything you want me to go over more? Or do you got this? Because that's the lesson for today. Everybody pretty good? All right. Other than that, I'll see you guys all tomorrow. All right, tomorrow is Thursday. So we're going into freshwater generation tomorrow. We will have a quiz on what we did today. And then the test is next Wednesday. All right? Everyone good?
Have a good day.
Have a good one.
Well, the freshwater generation, that won't be on the first exam, right?
No,
Okay.
just to save time, basically.
Okay. All right. Have a good day.
Have a good one.